Great. Well, I'm excited to introduce our next speaker, Dr. Jason Fries. Jason is an assistant professor of biomedical data science and medicine, and really is an expert in building and evaluating foundation models for healthcare, because Jason brings in such a fantastic knowledge, not just of the underlying technologies, but what the clinical applications and the challenges are. So excited to introduce Jason.
Great, thanks so much, Akshay. All right, so today I'm going to talk about innovation at the intersection of clinical and data-centric AI. AI is capable of absolutely amazing things, and the medical capabilities of models are really improving dramatically. But it's really useful to think about where we need this technology to go. So it's under that lens, it's useful to think about very complicated medical decision-making and how sort of state-of-the-art measures. So we've been studying tumor boards very recently. These are settings where complex cancer patients are presented to a set of oncology experts to make really hard decisions on what to do next. And if you think about a case such as an advanced lung case, a cancer patient case coming in, think about the kind of data you want AI to be able to ingest and reason over. You may want it to look at genetic mutations. You may want to look at pathology reports and radiology reports. You may want to look at a broader lens of history. And you want to situate that in a way that allows you to plan for the effects and impact of treatment. But all of that's today is actually quite difficult. You either have to prepare really arduously to go into these tumor board meetings, and the tooling and help and assistance is not up to the bar to look at things longitudinally, to find similar patients. It's very hard just to go to a medical record system and sort of talk in these abstract terms of finding similar patients. And so when we think about sort of AI and where we need it to be, it's extremely useful to think of electronic health records as multimodal timelines. This would be where rows are different modalities and columns are different observations over points in time. And it's really critical to take this broader lens to think about how the timeline itself is varying and interacting with the vast array of different types of modalities we capture about people as their health projects over time. And so this is critical because if we think about how today's AI models are built, they are, in fact, quite narrow. You think about image-only models, maybe you're incorporating some degree of language, describing a phenomenon at a single point in time. Our understanding of where radiology, pathology, and the many types of data captured about a patient is situated in their history is extremely narrow. And we've taken to calling this a missing context problem. And if we really have the ambition that AI will allow us to reason over not only short time horizons, but the degree of like months or years, then we really need to think fundamentally, what is the data we're providing to these models to learn from? And we're in a regime where it's really difficult for YouTube scale data sets to train coherent videos over seconds, right? So the ambition of thinking about humans evolve over years is, given the data we have, is a very challenging frontier to think about. So the future really needs to be thinking about these ideas of multimodal timelines as a unifying framework for retrieval, finding the information we need when we need it, interaction, how it serves the needs of clinicians and ultimately patients, and how feedback can enter that system to make it more useful. We have in the hospital today, Nigam Shah and his data science team have deployed chat interfaces over the EHR, but we want to be able to do increasingly advanced things with not only a single patient, but a patient population. So we want to find similar patients. We want to learn from large collections of humans and how they respond in a dynamic, interactive way where we can start capturing signal from the experts to start improving those models and the data. And so that's where I really land on the theme of this talk, and to some extent the theme of my lab, is that training data ultimately dictates the LLM or any generative AI's abilities, capabilities, limitations, and then biases. And so the kind of emerging consensus about how these models learn is we have a phase called pre-training. That's where we learn general knowledge. This is the insane internet scale types of training runs we see coming out of frontier models. This is where it learns the basic primitives of reasoning. We have this kind of middle stage called mid-training, where we're bridging distributions from pre-training to something that looks more like how we want to use the model. This would be the domain specification or specialization. And then we have post-training, which is a mix of supervised fine-tuning and reinforcement learning to really start training the model to actually be useful and to do the things that we want it to achieve. Now, the scale is often offered in all of the PR of frontier labs, and you really feel closed out as an academic when you don't have billions of dollars in compute to train models. But really the feeling or understanding that's emerged in many times is that quality is much better than quantity in many cases. And in careful, particularly in post-training, sort of careful domain-aware curation can build dramatically smaller, more useful data sets to teach a model to do something useful. And so this is an example. This version of less is more has showed up in like 10 paper titles over the past couple of years, but the theme is consistent, is that you pick a very tiny subset of data, in this case mathematical reasoning, and if you adapt a model using that data, you do wildly better than if you use the whole data set. And so it really shows that there is this place for teaching a model, and that quality and good representative data is extremely important to getting a model to doing what we want it to do. And I think that is extremely important in healthcare, where we are beset by data quality problems and biases and missingness. And so we really need to think about the regime by which we are producing data to teach the next generation of models to do useful things. And then I think this is really predicated at its heart on defining a feedback loop. That is to say, we are tied together in thinking about how we do evaluation, how humans and AI collaborate to do something useful, and how that feeds back into the data that is trained and updating our model, and how this cycle is sustained in the life cycle of how we deploy AI. And we have only barely started scratching the surface of what this immensely complicated, dynamic life cycle system would even look like in a healthcare setting. And I think that's what gets me the most excited when we start thinking about how we train foundation models for our next set of ambitious problems. So some previous research that I have been part of is thinking about training EHR foundation models, both what are called autoregressive. These are classic next word, next code prediction type models, but also time to event models. That is to say, in medicine, we don't just care what the next event is, we often care when a bunch of different things may happen. And so time is an extremely valuable signal for teaching models to predict and anticipate health trajectories. And so we have two papers that look at this idea of time as a pre or mid-training signal, both in iClear, that's a CS conference. And what we find is in general, models trained on time horizons at massive scale, using all of the, say, ICD codes available to you in EHR over the course of many years. You're able to beat state-of-the-art, that's random survival forest, and see much further into the future in terms of your predictive performance benefits. And that's on the order of like 1 to 2 years is how this is the now, this is the future, and these are broken into deciles of time points into the future. So the model sees more into predicts further into the future. The models are actually more robust as well. If you take a model, we called a foundation model called Motor. If you train it up until 2022, and then evaluated on 2023 data here at Stanford, we find that it's 10% more robust than competing models, and it actually changes out of distribution. If you take it to Mimic, it's a PhysioNet data set, it actually performs really better than state-of-the-art, or better than competing models as well. This is super important because we have a lot of talk and excitement around zero-shot EHR models. These are models that simulate possible future trajectories. Epic has made their Curiosity model, which does these giant synthetic timeline generation. Myself and a paper led by Suhana Bedi and with Nigam Shah have written a paper calling for new evaluation regimes in this type of model. We have pushed for new benchmarks that actually can measure longitudinal patient trajectories. These data sets are available today online for companies or research labs and universities who want to download and experiment not only tasks curated by us, but the models we have trained, making fully reproducible claims about EHR models. And then finally, we have been working for the past year and some change on building a massive multimodal data lake that Sylvia mentioned in her opening talk, funded by ARPA-H, in which we have 211,000 cancer patients of many aligned modalities. This is a visualization of their EHR embeddings, and it's a really exciting time to think about how we can use these latent representations to do better prediction and human AI teaming and all of these ambitious goals I outlined in the talk at the beginning. So this is a huge team. I'm the one up here, but there are a huge number of students, PIs, and TDS are a really amazing data team feeding us this stuff, and so we couldn't do any of this research without them. And with that, I open for questions.
Do we have any questions?
Great presentation, very much enjoyed it. My name is Judy Lee, I'm from AstraZeneca. So on the pharmaceutical side, when we work on clinical trial data, we have a large department doing data cleaning. Again, go back to your comment, I really like it, data heavily rely on the data quality, but when you work on EHR data, can you comment a little bit more on, especially from the academic side, like how do you guys like clean the data, just make sure that the data quality is good?
Yeah, that's a great question. I think this is an active area of research on what to do. Some of it is a mix of learned lessons of like things that we know institutionally leak outcomes or cheat, and so it's a lot of manual fixing of those problems. But I think there are more opportunities to borrow some insight from LLM data quality assessment, particularly at ICML. There were some papers, CS conference papers, on looking at sort of token level noise. And I think if you think about EHR as this timeline of sequences, you can start thinking about how you do data evaluation over individual instances, so models to tell you if the data is bad or not. So I think really we want to land in a world where we have this agentic feedback system where a human is working on data, making observations, and that doesn't become one-off insights or long plows to making code that does it. It's we're teaching a model to help us find bad data. And I think that's really, where we need to go, because EHR is extremely messy, extremely biased, extremely fraught, and I think there's a lot of great stuff there, so we need to figure that out. So. Yeah.
Hi, I'm Christoph from Genentech. My question is kind of related to what you just said. You talked a little bit about being about quantity and not quantity, right? How you want to make sure that you have like really good representative data. But in some situations, you don't always know what the whole picture is supposed to look like, right? So that means that like you kind of like go into the dark and you have to like figure out a way to make your data be generalizable, but you don't really know what the standard is supposed to look like. So how do you go around like potentially addressing that kind of issues?
Yeah, the unknown unknowns, like it's really hard, right? I sort of take an engineering benchmarking perspective, is that we need to measure better and we need to have benchmarks that other people are participating in building. Like it's easy to get blinkered, particularly as a researcher, to thinking you have an understanding of the lens of a data or how it's generated. And that's why you need to have, benchmarking is a collaborative, fundamentally process that you are called out and held to different standards. And I think that adversarial process does lead to better, more robust models. Now, will they lead more fair? Will they lead more equitable? That I think is a longer, more challenging conversation, but that's the direction I think we need to go.
Fantastic. We thank Jason once again.